Okay, my name is Grimm. I'm a software developer since 1999. Since 2016, I'm just a C++ trainer, independent C++ trainer. 70–80% C++, the rest Python. So, during my trainings, I give a lot of talks or I give a lot of classes about concurrency. And you know, a lot of stuff can go wrong. Okay, I gave my last class from Monday to Tuesday, only concerning or talking about concurrency. Let me tell you a story a little bit about my experience the last 10 years. Okay, I have this one. Okay, best practices for concurrency. These are my 4 topics. General remarks, what is multi-threading specific, meaning C++ specific. I cannot tell much about parallelity because it's not available in C++, so there's no best practice until now. And at the end, a little bit about the memory model, which is kind of scary. I will also say things which seems to be quite obvious, but I will make it short, only to be complete. Okay, let's start. I have to look general ideas. Okay. That is my first general idea, quite obvious. If you do some multi-threading stuff, do code reviews, make pair programming, because this stuff is terribly difficult. That is a simple example I often present in my classes. I just say, there's a data race inside. Where is it? Only 5% of the people actually find it. I use this as a good way for me to go for a cup of coffee. Have a look what I did here. My idea is to implement a reader-writer lock. I have 8 readers, 2 writers, and the key idea is at one point in time, a lot of readers can read, but only one writer should write. Okay. So how can it be done? I use a kind of a shared time mutex, which we have since C++14. I put it here and here. And that's the reading part. You see, if I put my Talbot mutex in a shared lock, it becomes a shared lock. If I put it into a lock guard, it becomes an exclusive lock. Here you see that the reading is overlapping, which is fine, because that's not an issue. Only the writing part is critical. What's the problem with this program? The problem is stuff which seems to be a reading stuff is actually writing stuff or updating stuff. Let me only put Bjarne in front of all the other guys. So I want first to know the telephone number of Bjarne. I did it, and you see it here. Could happen. These are threads. Now you see something strange. Bjarne has the telephone number 0. Why? There was no Bjarne in the telephone book, meaning Bjarne was created with the default value of int, which is 0, which means, and that's the key point, this is not a reading access, that is a modifying access. Concurrent reading and writing, data race, undefined behavior, catch fire semantic. Your PC can catch fire, literally. So you should not do that. Okay, but as I mentioned, only 5% of the people which program, which use at least 15 years C++, so they know what a map is and what the behavior of a map is, but they forgot it. Quite easy. Okay, that is also kind of trivial, but I can draw an interesting conclusion. I played a little bit, and what I wanted to do was to sum up 100 million elements. I did it in a straightforward way with a for loop, and you should not do that in such a way. So I did it also with std accumulate, which is understood kind of similar. Okay, I did it in a single-threaded way, but you know, I have 4 cores. You should not do it if you have 4 cores. So what I did was extremely straightforward, but extremely simple or stupid, to be honest. I just put a lock guard around my summation variable. I had 4 threads, and I did it, and I became a lot slower. Of course, contention, synchronization costs so much, but we can do better. Or we have atomics. Let me make it with an atomic. Sum is atomic. And even let me make it with an atomic with relaxed semantic. That's the best I can get. I was a little bit faster, but not really as fast as in the single-threaded case. Of course, contention, synchronization is a quite heavy process. So what I did at the end, which is my advice, do the stuff locally, and then do only the synchronization with only synchronize using a lock or something like that. Now it becomes quite fast. Here are the numbers, and you see that's the single-threaded case, and that is the case in which case I used 4 threads, and I was 4 times faster. No, only 2 times faster. What happened here? I was totally astonished, because this was a job which was calculation-driven, no synchronization or minimal synchronization, so I would expect 4 times performance improvement, or not. What's the problem? I forgot, I looked at my CPUs, you see, a few of them were idle, a few had 100%. My bottleneck is the RAM. All threads have to read from the same RAM. That's the bottleneck. Though my cores are quite fast, but my RAM is too slow, so what can I do? So, you see, minimize sharing, and sometimes you will not get the 4 times performance improvement, but only double of it. Okay, this is quite a familiar rule, but you can draw also interesting conclusion out of it. This is Amdahl's law. What does it mean? If your program of 50% of your program can run in parallel, you can at most expect a 2 times performance improvement if you put arbitrary number of CPUs on your problem. Okay, what does it mean? And that is the picture I want to mention. This means, have a look, 50%. That means with 16 CPUs, you will get to the peak. With 16 CPUs. So it makes no sense to put more CPU power on your problem if your program can only parallelize 50%. If it could be parallelized, such as here, have a look, 95%, your peak will be around 4,000 cores. I don't know if you have them, but you see, only if you have a big amount of stuff which can run in parallel, it makes sense to buy a few processors. And that is the key conclusion from this picture. Okay. What I also often mention is, when you program multi-threading, when you do concurrency, use all tools you can get to check your code, to verify it. And there's one which is great. I hope you know it. If not, you will know it in a few seconds. That's ThreadSanitizer. It's available since GCC 4.8 in Clang 3.2, so you have it. And what it does is it analyzes at runtime if you have a data race. And you know we don't want to have data races. And that's the way to do it. Minus F sanitize minus G. Then you will get human readable text to show you what was going wrong if. And here is a use case. This is an example one of my participants produced during the seminar. That is a kind of a ping-pong game. I have one thread which says true, and the other thread says false. The play goes for 50, has 50 iterations, and each thread makes a notification if the thread is done. You see, notify 1 goes to wait here, and the other way around. So ping pong, ping pong. If you want to look, if you want to know where the data race is, it's quite easy. Mutable shared state. Only look at mutable shared state. And what is mutable and shared here? Of course, counter. I have a concurrent write and read. That's not good. Now I executed this program, translated it, as you can see it here, and that happened. False true, and now the warning, line 30, and here it goes on, false true, false true. So it's quite easy. You can prove that there is a data race inside, not the other way around. Okay, but that's not all. I'm also a big fan of CppMem. CppMem, to be honest, is quite difficult to use. You have so many ways to configure it, so that's just the default configuration. CppMem is a tool in which you can put in a kind of C++-ish way to express atomics and concurrency. Then you let the program run, and CPP, that's a static code analyzer tool, CppMem calculates all possible interleaving during this program, which are possible because of this program. So all of them. Into each interleaving, you will get a graph with GraphViz, annotated with typical properties of the memory model, synchronized before asynchronous, synchronized with data dependency, sequential consistency, modification order, read from, and so on and so on. In particular, data race. To each execution which is possible, you will get this graph. And then if something goes wrong, such as here, the text is red because I have a data race. CppMem, extremely valuable tool. Here you have a look, x equals 3, and x is written, and x is read here. That's the data race. And here you see it, dr, data race. That's the graph, one of the graphs which corresponds to this program. I forgot to mention, with previous consistent and next consistent, you can go back and forth between each interleaving, which is possible. This tool gives you two big benefits. First, you can check your program. If it's fine, it's not fine. Okay, you see if it's not fine. Second, if it gives you a deeper insight in the memory model, which is really, really hard. Okay, I played the last years a lot with this tool to get a deeper understanding. Okay, let me continue a little bit. That is a simple program. It uses thread, and here I have a data race. Now I will translate this simple program, which I presented here 4 years ago, and it had a data race. I was not aware of it. Maybe sometimes error happens. Okay, let's have a look here. You see x equal 2000, and here I read x. There's no guarantee that this x will not happen after this x equals 2000. Therefore, it could happen concurrent. That's my data race. So the data race is on x. This program translated to CppMem looks a little bit special. This is a thread. It starts here, it ends here. This is a thread, starts here, ends here. And then you see here the short notation CppMem. And that is the graph, which this is one of the execution which is possible due to this program. And that is the buggy execution. You see, dr, data race. X equal 2000 it happens at the same time such as x is 0. This one has a data race with this one. That's CppMem. It's kind of difficult. I have written a lot of blog posts about it, maybe 20. Maybe it helps you to get a deeper understanding of the stuff. It is now used in Great Britain to teach the students the memory model because it helps you to visualize these strange effects. Okay, so general rule, use code analysis tools. Okay, that is easy, you know. If you want to have fun with multi-threading, use shared mutable state. Then you are open to data races. If not, you are quite fine. A requirement for a data race is shared mutable state. If not, fine. Okay, so what's the problem? Quite easy. Make your stuff const. No data race is possible. You have only to guarantee that your data is initialized in a thread-safe way. And there are many possibilities in C++ to do it, in particular in C++ 11. Just initialize your data before you share it. Quite simple. Second, make your data const expr, meaning it is evaluated at compile time. There's no threading issue there. Third, so it looks a little bit ugly, but it's possible. I want to have the guarantee that this function, only once function, is executed exactly once. And I can do it in such a way. I wrap it in call once, and I synchronize it with the once flag. Therefore, even if I invoke func 2 times, only one invocation will succeed. I don't know which one. That's the guarantee of call once combined with the once flag. Okay, and that is quite easy. Just use a static variable with block scope. And the C++ 11 runtime guarantees the initialization is thread safe. Okay, a few ways to initialize something in a thread safe way. Okay, let's continue with immutability. We have pure functions. You know, it may be from Haskell or from template metaprogramming. We have pure function. What is a pure function? It's a total simple concept, but it has a great benefit, in particular in multi-threading environments or concurrent environments. A pure function is a function which always produces the same result when given the same arguments. What's a pure function? Maybe sinus, sine. Sine of 5 is always the same. I don't know what, but it's always the same. But of course, time or random should not be pure. A random function which will always produce the same result is strange. So there are pure and impure functions. Okay, further benefits of pure function. They have no side effect. They will not change something outside the function body. They will even not change the global state of the program. And to be honest, these are the kind of functions you want to have, not only from the concurrency perspective. Why? It's easier to make correctness proof because you can look at the function isolation. The function will not change something in the environment. It's quite easy. It's quite easy to test and to refactor. Do you ever thought about how to test what should be the expected value of your random function? It's quite difficult, I assume. But with Syn, you are quite fine. Okay, then, and that is often used in Python, not so often in C++, I don't know why. If you know that a function will always produce the same result, and the function, the execution of the function is quite expensive, just remember the result from before, put the value in a map, another map, and return the value. That is quite often done, in, as I mentioned in Python, it's called memorization. You can do it. With random, you can of course not do it, only to show the difference. And that is the main point which I want to make here. A function which is independent of the environment can be reordered. You can even put it to a different thread. You don't care. You only care about the result, not when and where it was invoked. So, it's a pity we have no pure function in C++, only something similar. First of all, you can just implement a pure function. That's fine. This function is pure. Okay, will not change anything outside the function body. Sorry?
Yes.
Is it? Thanks. We should synchronize. Okay. Meta function. A function which is executed at compile time is pure. That's the reason why C++ template metaprogramming is a pure functional sublanguage in the imperative language. So this stuff, it's not nice, but it's pure. Calculating the power of a number at compile time with this template metaprogramming stuff. And that is the way you should go. Just use constexpr. If a constexpr function is used during compile time, it's pure. And here are 3 ways to calculate something in a pure way. So a constexpr function is, if used at compile time, such as here, I enforce it, pure. No threading issues. To be honest, the function invocation will be replaced with the result, so there's only value if you look at Godbolt. Okay, these were my general ideas. Let's go further with multi-threading. That is totally simple, so I will make it extremely short, but I have to mention it. Don't use threads, use tasks. Okay, there are a lot of reasons. The main reason is here you have no shared state. And here maybe I have an issue, I don't know. And you have a safe channel between the promise and the future. You don't know if there wasn't thread started or not, but you don't care, because here you care about the thread, and here only you care about what should be executed. So it's a kind of an abstraction. Okay, what further? A thread can only return a value, but here you can return values, notifications, and even exceptions in a thread between threads. Okay, quite good. There's a pity with tasks, and therefore I'm not sure how the future of futures will look like. There's a lot of discussions in C++11, and as far as I know, the discussion continued last week in San Diego. Maybe we will get something like here, but I'm not sure. The idea is, which is a little bit better about futures, but that is, to say it once more, the future of the futures. With futures, we should have continuation. We should have the concept, when any of the future is done, continue the next future, or when all of the futures are done, continue the next future. And that is nowadays the discussion, how it should look like in the future. Okay, that was fast because I think you know it. But there are a few details to Stud Async which are not so nice. Looks nice, this program. It has a nice feature. Stud Async has a nice feature. Don't use fire and forget future. First of all, what's the fire and forget future? It's a future promise I invoke in place, and I have a kind of temporary future which I will not bind to a value. That is not a fire and forget future. I have a handle future to the result. That's a fire and forget future. Is nice, or? No, there's an issue here. You can look at it from the positive perspective. You don't have to call join or attach, because it will automatically be joined, so you're fine. But you can also look at it from the different perspective. This call will block until the promise here is done. What seems to be concurrent is synchron. It's a sequential execution. Have a look here. Here I use one fire and forget future, second fire and forget future, and at the end I say main thread. Okay, fine. If you calculate, then you should assume that first main thread will be displayed, then second thread, and then first thread, because the first thread sleeps 2 seconds, 1 second, and this one doesn't sleep. But if you look carefully, it will be executed exactly in the way written. Why? This call here is blocking until 2 seconds are gone, because it blocks in the destructor. You can see it as a feature, or maybe it's something different. At the end, this program takes 2 + 1, a little bit more than 3 seconds, because it's a fully sequential program. To overcome this issue, quite easy, just give the futures a name, and then the blocking point is here, at the end of the main scope. if first and second goes out of scope. Okay. For me, it's not so bad, this behavior, but there are a lot of people which complain about blocking futures. At least you should know it. Okay, now something. Sorry, that is wrong. That is not best practices, kind of. That is stuff we will get with high probability with C++20. You know, std_thread has a great feature. If you forget to join or detach a thread, therefore the thread is still joinable in this destructor, you will get a std terminate. And these are the last words of my thread. To be honest, I don't like this error message. You have no clue what was going wrong. And that will stop with C++20. I have to say a few words. I met Nikolai at CppCon 6 or 7 weeks ago. He asked me, what do you think about the new G thread? Nikolai, which will give today the closing keynote. And I said, I don't know it, but now I know it, you see. Once more. Your program dies because you forgot to join the thread. That means when this guy goes out of scope, you will get that. Okay, what can you do? Just replace T with G thread, and that is all. That is an automatically joining thread. That means if the thread is still joinable in the destructor, join would be called. I have to add one additional remark. There's an additional feature to this G thread, which I want to mention only to tell you the story. First, it was not called G thread, it was called E thread. Why? It's also interruptible. What you can do now is to interrupt a thread, which of course was not possible because interrupting a thread is a kind of a dangerous endeavor. You know, if the thread has a lock, you have a deadlock, for sure. Okay. So what you can do, you have a receiver which can ask if it was interrupted, and then he can react the thread if you like or not. It's cooperatively. It's not you don't enforce it. And then a few weight variation of the condition variables have also a variant which you can use to interrupt it. So you cannot only wait with notification, but also with interruption. Okay, that is the sender. He just says interrupt and returns if he was already interrupted. That's all. And here's a small example which you can use with C++17. That is a thread, G thread, you see, non-interruptible. Here's nothing is special. I could even use, no, I could not even, but kind of use here thread. But here I use G thread, and here I have an interrupt token, additional constructor argument. And the key point is, here in my body I ask if I was interrupted. Then here's my main thread, and I say interrupt to both of them. But this guy will not react. He has no interrupt token, so he cannot, out of I token, he cannot be interrupted. This will interrupt, react, and just return. Onto the difference. Now have a look carefully. 1 second. I sleep each time for fifth of a second, you see. At the end, that is the output. Interruptible, not interruptible. Then I say interrupt both, and only the non-interruptible will continue until the end. So it's cooperatively interruption, not preemptive. Okay. That's the future. But the past is more exciting. You know, condition variables, there are a lot of ways to shoot yourself in the foot. Really, a lot of ways. And to be honest, I don't like it because it's such a kind of a similar concept. Sender, receive, producer, consume, kind of synchronization between threads. But there's an issue. Okay. We have two nice phenomena called spurious wake up and lost wake up. First, the issue is a condition variable has no state, no memory. Okay, what's with this both? We have a spurious wake up. Now a strange story, but to be honest, that's true. Imagine you sleep, you will be awoken, it was not an alarm clock, it was your cat. Could happen. That's a spurious wake up. What will you do in real life? You look at the alarm clock and you recognize, oh, it's not so late. We don't talk about the cat, only about the alarm clock. That is what you do. That's your state, your alarm clock. Okay, then you are a little bit thirsty because you were at a social event. You go to drink something, and in the meantime, the alarm clock goes. You go back to bed, and you sleep forever. Deadlock, because the notification will never come. Don't laugh, it will happen each second time if I don't use this stuff here, which I will come in 5 seconds. That is a lost wake up, because the standard says, wait will only recognize this notification, which will happen at the same time, whatever same time means. If not, no memory. That was it. And what will you do in normal life? Before you go back to bed, you look at the alarm clock once more. Maybe it's too late. You have to stand up. I don't know. And that is the reason why you should use condition variables exactly in this kind of structure. I use it here. That is my alarm clock. Meaning, if I'm awoken here, I know, true happened already, so far it's time to stand up. If not, I know it was a spurious or lost wake up. Just, you have to use it in such a way. And compare this with the synchronization which you can do with in future and promise, to be honest. Promise in future. That is the stuff I want to have. Not that stuff here above. Such as logguards, uniclog, state, and whatever. I only care about this one, but with condition variables you can shoot yourself in the foot. But that was the easy story. It goes on. Maybe you think, oh, that's a Boolean. We have atomic bool. If I use atomic bool, I can get rid of this critical region here. No? Fine. Another possibility for a deadlock. This, what looks like one line, is actually a two-liner, and that's the problem. Let me write it in the way it's implemented. It's kind of such. In the outer part, you check if data, I assume here that data already is atomic. You see, load is atomic operation. And here I have just atomic, which I put to 2. Here I assume, here I check the precondition, which is I look at the alarm clock. Is it too late? Can I go to bed? And then in the inner part, I do a wait without condition. That's the way it's internally implemented, kind of. And if the notification goes here, it will exactly land here. And that's the time I was not aware of the notification. There's a small gap between here and here, and if the notification will go in this point, it is lost, of course. Therefore, you have a deadlock. Meaning, with atomics, you will be free of a data race, but not of a deadlock, if you want to optimize. Okay, I want to make one additional point. Yeah, my point is that this curly brace must synchronize. They must build a kind of a total order. Therefore, there cannot be anything between here and here. They are executed one after the other without a time gap. I don't know how to say it in different words. Don't be too clever with condition variables. Okay. Okay. That is crappy code. Why? Because of a lot of reasons. Okay. We should improve it. First of all, a lock is for me just a key to want to go inside a room. And The other part is, of course, the door, which I have to open or close. Okay, what can happen here? I want to go, I'm inside the room and I die. Exception. Therefore, I have an unlock. No. Then I'm quite, how should I say it? I'm totally sportive. What I will do, I leave the door and use the window. The next way of a deadlock, you know? There are different control flows, and I forgot to unlock. That's a deadlock. Okay, what can also happen? Now I stop with my picture. What can also happen? If I'm here and getVar locks this same mutex once more, which is in my case not a recursive mutex, it's undefined behavior, and you can expect deadlock, but it's undefined behavior, so forget your program. If I'm in getVar and I lock a different mutex, I can do it, with a little bit of interleaving, I got a different kind of deadlock. What can also go wrong? Maybe that is right, but I have a new coworker and it's dynamically linked and he changed getVar. I have no idea. So this code is terrible. Most of the problems can be solved here, but not the last 3 ones. Here, it will always be unlocked here if I die or if I leave by going through the window. No problem. But there's a big issue here. And here, once more. I call the rule minimal locking, or never call unknown code while holding a lock point. Never call unknown code while holding a lock. That's an anti-pattern, not a pattern, anti-pattern. A pattern to shoot yourself in the foot. So what will you do? Let me continue my picture. I want to go inside. I want to have the lock, but the one inside is sleeping. Could happen. I don't know this function. Could happen. What I suggest to this guy here inside, sleep outside. And that's all. Only the critical stuff must be done inside. Quite easy, or? That means I just create a local variable outside, make the assignment, and only protect what should be protected. And that's the assignment point. Reduce your critical minimal locking or reduce it to the minimal amount of time. And that's the stuff you want to have. You want to have concurrency. Okay, quite a simple rule. And that's the next rule, which is quite obvious. Therefore, I make it short. If we want to eat something, and to eat something, we have a plate of noodle. We need 2 sticks. I will grab it right, left. You will grab it right, left. And then with a little bit of luck, we will get a deadlock. Because you have the right one. Yeah, I have the right one. I want to have the left one. You want to have the left one. And you know, threads are totally egoistic. We will starve to death. And that's this situation. You want to have more than one lock, and with a little bit of interleaving, you will get a deadlock. There are 2 ways to solve this issue. That's the 14 way, sorry, that's the 11 way, that's the 17 way. The 17 way is, here I'm not locking my mutex, but this lock guard is an atomic try to lock both of them. So I want to get the forks not in this way, but in this way. I get both of them or none of them. And that is a loop until I succeed. That is the way I should do it with C++11. Here's the critical region. And that is, for me, nicer. That's the way you can do it directly in C++17. Just use a scope clock with mutexes. And that's a while loop in which a series of try locks are applied until they succeed. Okay. Now we come to the fun stuff. Okay, Mom, I'm just in time. First of all, my daughter, Shili, is responsible for correcting my typos. Maybe they find a lot of them, but not all of them. But that's not my point. My point is, she saw this slide, and her reaction was, remove it, it's totally ugly. She was right, but I want to talk about ugly stuff, so I'm also right. That is log-free programming. That is the people say about this stuff. Herb Sutter, playing with knives. Only screenshots from talks, most of them from CppCon. Then Anthony Williams, how to shoot yourself in the foot. Great. To this one I will come later because it's my favorite. Here, writing log-free programs is hard. Correct log-free programs is even harder. You're right. He's right. And here, German guy, Hans Böhm, he talks a little bit about ugly side, and I'm not even going to talk about memory order consume. Do you know the story about memory order consume? We have 6 different memory orderings. One of them is called memory order consume. Don't remember it because it makes no sense. I will tell you why. Okay, it was standardized with C++11. One of the GCCs, I don't know, 2013, 14, I don't know, actually implemented it. But they recognized there was an error inside. So they replaced consume with acquire, which is fine, which is a little bit stronger. And that is the official wording, so memory order consume is being erased, and the use of memory order consume is temporarily discouraged. They cannot fix it, I assume, until now. I had a discussion with Michael Wong 2 years ago. He said to me, they are quite enthusiastic to fix the issue, but now you see, I'm not sure what's the state with C++20, that is 17. It will take, in the best way, 9 years to implement it. So it's kind of difficult. Okay, oh, I forget it. That's my favorite quote, which I always give in my multi-threading classes. You have to learn it by heart. Forget what you learned in kindergarten, don't share. The most important sentence to concurrency. No, that's quite easy. If you share, you're in trouble. Okay. You see it. Forget what you learned in kindergarten. Oh yeah, something like that. Okay. Okay, there are a lot of issues. I will not even mention the really, really ugly ones. This one that is ugly enough. I should put it in this way. ABBA, what does it mean? It's quite easy. You go by car, there's a traffic jam, it's red, you have to wait, you are totally bored. So you look at your smartphone and you look up and the traffic jam is the traffic light is still red. So it was red in the first place and in the second place, and because of that you oversaw that it was green between. That's ABBA. A-B-A. You look at the world, it is in the state A. You want to do something, but before you do it, the world should still be in the state A, and you oversaw that it became in between B. That's ABBA. Quite simple. And what you can do with ABBA is quite nice, and that is a really big issue with stack, with a concurrent or log-free data structure such as stack. Have a look here. I have here a simple stack, top A, B, C, and I want to remove A. I want to make a new head. Quite easy. What I do, I store A and I store B because I want to remove it. Then another thread kicks in. Another thread removes A, it removes B and deletes B, and then he removes A, he recycles A. Okay, now the stack looks like here. B is gone. B was deleted. Now thread A comes back, and there are primitives such as compare exchange weak or strong. It sees, oh, A is still head, fine. And now I make B to my new head, but B was deleted by this guy. Okay. And that is ABBA, and that's really, really issue with concurrent data structures. You program with concurrent data structure often this way, like a transaction on atomics. what's the state here, what's the state now, and do something in between. And before you want to commit your change, you check. And if the check gives you the result you expect, you publish, but something changed in between. That's the other problem. Okay. Okay, but we have a few patterns which work with atomics. And I only want to show you these 3 ones. The first one is sequential consistency. The key point here is, do you see what I simulated here? A kind of a condition variable using atomics. I have here data ready store. Here I put data ready to true. Here I wait until data ready becomes true. And I want to have the guarantee that this will always happen before this, because this is not atomic. It's just a vector. Okay. So what I have here is I have sequential consistency. That means this load waits on this true and establish the additional guarantee that all what happened here before is afterwards here visible. That's fine. Therefore, I have synchronization. So I use atomic with sequential consistency to synchronize non-atomics. Okay, you see? Okay, that's fine. I can even improve it because a store is a release operation and a load is an acquire operation. I can use acquire release semantic. And the same argumentation goes here. This acquire synchronizes with this release and establish an ordering guarantee that all what happened here before is visible here after. And that's all I want to have. That is the way locks and unlock operation works under the hood. Okay. There are a few additional patterns which are quite simple, and that is if you have an atomic counter and you don't care. You only count, you only care how often it was incremented, but you don't care in which order it was. You can even use memory order relaxed. Memory order relaxed under the hood means the only guarantee you have is atomicity. All other guarantees are gone. And you see, that's quite easy. I have a thread here. I have, to be honest, 10 of them. Each executes from 0 to 1000 and adds the counter to this shared counter count. And I will always get the value 1000. And the key point is this memory order relaxed is cannot go after this join and not go before the thread creation. It's a kind of a border, and I don't care in which order they happen. I only care that all of their increments happen. So atomic count is also kind of easy concept. Maybe I can make it more visual. You know the shared pointer? There's an atomic counter. Upwards, it's a relaxed with relaxed semantic, and upwards, downwards, it's with acquire release semantic. Because downwards, you want to be sure that you delete the resource at the right point in time. But upwards, you don't care if it's 5, 10, or whatever. Okay. Okay. Don't reinvent the wheel. If you want to become famous, but not maybe for the reason you want to be famous, invent a log-free data structure. There are few of them, but just use them. That's terribly difficult, terribly. I told you about ABBA. That is not the most difficult issue. The most difficult issue in C++ is if you have something like a stack and you want to delete something, when can you delete it? That's the issue. Releasing memory, because you never know if another thread is just using this node you want to release, which is not so good idea. So memory release, releasing memory is by far the most difficult part with this lock-free or wait-free data structures. Not the upper problem, that was easy. You can handle it. So don't do it, meaning use boost lock-free or concurrent data structures. They have a bunch of different concurrent, lock-free, and thread-safe, and so on data structures. Here is boost. There's a queue, lock-free, multi-producer, multi-consumer. There's a stack, multi-producer, multi-consumer, and there's a kind of a single producer, single consumer data structure, which is wait-free. The difference between lock-free and wait-free, because I mentioned it, is with lock-free, you have the guarantee that your program will end in a finite number of steps. The whole program. Not each thread, the whole program. With wait-free, you have the guarantee that each thread will end in a finite number of steps, whatever finite number of steps means. That's the difference. So wait-free is the stronger guarantee. Okay, and that is concurrent data structures. Contains a lot of containers, stacks, queues, periodic queues, ordered list, ordered sets, maps. You see, there's a lot of stuff inside. libcds is the official name as far as I know. And I think now I'm done. Okay, yeah, I'm totally done. I have to say questions. So because any questions? We have, I think, maybe 8 minutes. 8 minutes. No, it's 8. Was it too easy or too difficult? I'm not sure. I do this a lot, so I'm quite used to it, but it could be kind of difficult. It can be kind of difficult. Okay, if not, I will be here until for the rest of the day, at least. Okay.